repeated measures, replicated measures, replicates, same thing. So the example that I use, thermometer, let's just draw a big box. Could have been easier. Okay. Eight people, yes. So measuring temperature using the thermometer that I'm testing. So I'm going to get 8 different temperature readings. So that's my first try. Now I'm going to do it one more time with the same 8 people. And if my thermometer is doing what it's supposed to do, there has to be consistency between the two sets of measurements. Do we agree? Are they going to be exact in terms of measurements? Let's say the first person recorded 99.6. First time I took the temperature, let's say 30 seconds went by, I got my second measurement. Am I going to get the exact same 99.6 after 30 seconds? Maybe. Could it be different? Yeah, it could be different. Let's just say 99.5. Doesn't have to be different. Likewise, the last person, 98.4, perhaps 98.4. Clearly, there are going to be variations in the measurements, but if the thermometer is working properly, the first set of measurements, second set of measurements should not be significantly different. Agreed? That is repeated measures. Perhaps we'll do an example on this, then we can go to the second case, which is within subjects. And you will see soon that both of them are doing the exact same procedure. The scenario is different. Yes.
So would the 99.5 count as a repeated measure, even though it's different, or
Yeah.
would that?
Measure 1, measure 2, repeated. Measure 1, measure 2. So 8 measurements prior, 8 measurements after. I'm just going to use that as an example, unless you can come up with a different example. Do you want to? Wow, no. Okay.
Some arbitrary company named 10 Scientific is testing the accuracy of the US thermometer model. So they record temperatures of 8 participants twice between 30-second intervals. First time, 8 people recorded the observations. Second time, same 8 people recorded observations after 30 seconds. The questions that we want to answer, is there a statistically significant difference between the 2 trials? Is the thermometer consistent or reliable? When I first started, can I raise this picture? When I first started hypothesis testing, I wrote steps. What is the first step? You can look, you should know this, you did the homework. Very first step. Definition and starts with the letter A. Very good. Assumptions. Assumption is something that I will tell you. Why are assumptions important? If you violate the assumption but continue with the test, and whatever conclusion you have later is incorrect. So you've got to be careful when you have to perform a test. Ask yourself, are the assumptions satisfied? No. We are going to assume that the assumptions are satisfied. From experience, I know that this sample is not going to violate the assumption. So first sample has to be normally distributed.
each observation is independent of other observations within a group. In our case, the group would simply be a trial. What do I mean by that? Let's say, hypothetically, these two participants are from the same household and the temperatures are normal, but let's say they've been exposed to some sort of an infection, right? So these two participants are then connected. Yes, so within a group, the observations have to be independent. They must follow normal distribution. In other words, data cannot have skew. So no skew. Same thing. For this test, the sample has had observations. In other words, earlier I corrected Olivia that she made a mistake when she said different patients. So in this case, I'm going to measure the consistency of the thermometer 30 seconds later. I'd better get it from the same person. Agreed? I can't get temperature from Mantis and 30 seconds later, I go and record it from Olivia and put it in trial 1 and trial 2. That will not make any sense. Well, it's kind of silly to what we're trying to achieve. Good? Okay. There is no way in reality could we expect the observations to be exactly the same. They're not. Given all the variability, we want to know if our thermometer is consistent. Let's see. First step, definition. It is very important on how you define the difference here. If you don't define it properly, later when you make inferences, you will have challenges. For this problem, not a big deal, but within subjects design, usually you have to be careful on how you define the difference. So I'm going to use the letter D. It's common notation. Uses D. Also, difference between trials. No alternative. I want you to tell me what the null and the alternative should be in terms of D. Think about it. Now, a long time ago, Alison gave us an example. Average time spent on TikTok by a student is greater than 3.82. 87. Okay, so that was the alternative. There we used mu. We made a claim about mu. made a statement using D, I want you to come up with a statement using D for this problem. What should D be? If I want to answer that, or if I want to test whether there is a difference or not. Alison,
So what's that?
okay. Close, close. You know, I'm special, I gave you a new name. So go ahead, Alyssa.
Maybe would want to be that not average, well, I guess you could say average, the average of temperatures is over versus over like 95. I mean, you have one that's under 95, but average would be greater than that.
Okay. But we are taking a difference between the first and the second one.
Maybe saying that if it's more than 1 degree off from trial 1, then it's statistically.
Okay, you're going in the right direction, keep going, okay? So off by 1 degree, then it is a significant difference, okay? Any other answers? Yes, Caroline?
The null hypothesis could be D is less than or equal to a certain amount. We determine the threshold makes difference is significant, and then H1 is greater than. With H1, that would indicate a larger difference, indicating statistically significant difference.
Okay, that is also a correct answer. Anything else? Jacqueline?
For the null output, there's no difference in measurements in the trials. Like, so it would just be unequal because it could be below or above and still be a major difference.
Very good. Keep it simple, right? No, no difference. Alternative, there is a significant difference. Well, I'm writing it in words, but if I have to put it in terms of D, not just D, rather the average difference equal to 0. Versus the alternative that the average difference is not equal to 0. Do I find any of the other answers to be incorrect? No, Caroline, Sophie, they gave me the correct answer, but it's like making things harder, you know, unless there is a reason or a basis that you have to look for that 1 degree difference, it's not needed. All I want to know is there a difference? Is there not a difference? Good. And do pay attention, I am not looking at just D, rather the average of differences. Because I'm not looking at a single value. How many do I have? 8 of them, right? So you have to take the average. With me? Okay. When in doubt, you can always write it in words, then put the expression. So I'll write the expression again, one more time here. No. Mu is equal to 0, alternative, mu not equal to 0. A case like this, more often than not, is a be two-tailed. Within subjects, it could be two-tailed, right-tailed, or left-tailed. That's for the next example. Mu is the average difference. The next step would be to pick an alpha. What should we use? 0.05, 0.01, 0.1. You can give me one. Answers do you want to pick?
0.05.
0.05. Okay, step 2. We are picking alpha to be 0.05 or 1. Just pick 1.
Or 0.05.
Okay. Step three, we collect the data. We use the data to find the test statistic. We've already verified assumptions. There are ways to do it, but from experience, both of them are in fact normally distributed mostly, and I make sure that they are independent observations. Okay. This is a part where you have an option. Either do all the calculations manually or use the calculator and make things easier on yourself. Yes, so the choice is yours. So if you want to struggle, go for it, but calculator is better. We have the technology, let's put it to use. So in your calculator, that button right there, start, is crucial. After that, we have bars. That is a place that we have seen before. That's where we had inverse t to get critical values. So press start. The first option there is edit. So select one. And what does that remind you of? Those three columns, is anything coming to your mind? I heard it. Someone said something. What does that remind you of? That's green.
I don't know what it reminds me of, but is that where we're gonna put like the trial or?
No, that's exactly where we're going to put the data. Does it remind you of anything? You use it quite often. Spreadsheet. Instead of a spreadsheet, you simply have a basic table, bunch of lists. So start entering trial 1 in list 1, trial 2 observations in list 2. I will do the same. And do make sure that you enter observations carefully. It only takes one mistake for everything to go right. Okay. Good. So press second mode, exit. Back to start. In go to the right using the arrow, and you will see count. The very first one is 1 mass starts. 1 mass starts is going to give us mean, standard deviation, all that good stuff. So I'm going to pick 1 mass starts, find the mean of the first list, in other words, the average for the measurements in trial 1, I got 97.625. If it likes to use the letter N to sample average, X bar M, one and the same. Going to round it to 2 decimal places. The fourth row with numbers 1.874 is the standard deviation. For the first trial, just for practice, try the second trial game. If you simply choose one and hit enter, it is going to give you the statistics corresponding to the first list, always. You've got to specify the list name, in this case, L1, L2, etc. So over to calc, 1, second, 2. Blue button followed by the number 2. If you have the fancier version of the calculator, it probably says list, freak, calculate. So put L1, skip, and then calculate. So L2, 97.36 and 1.37. Good. Okay. For a minute, I think, no way, they could be the same. I didn't come up with the data so that they're exactly the same, defeats the purpose. So 97.63, 97.36, not the same, but pretty close. By all means, very close. Yes, sure, I can stop right here, pepper back and leave, but what works here, they're not working in a different setting. There has to be a scientific process. That's where statistical testing comes into play. I know what the answer will be already, but let's just do the process. So we don't simply want the mean and standard deviations for the individual samples, rather we want the mean standard deviation for the difference, correct? Yes. In our claim, we have the average difference. Whatever we are testing for is for the average difference. So go back to the table. Move over to the third list and go up by pressing the up arrow and simply type second 1 minus second 2. In other words, L1 minus L2. In this problem, it doesn't matter as to whether you do L1 minus L2 or L2 minus L1 because we are doing a two-tailed test. Good. Hit enter. It will automatically populate the differences for each of the observations. Good so far? Now, again, practice. Find the average for me. Average standard deviation for the third list. Yes.
It's giving me an error when I try to do the L1 minus L2. I don't know where I'm supposed to type it in.
So second, mode to quit, start, over, out. One last start, second, 3. The first value that we got or get using the data is M, average difference. This is from sample. If we round it, I can round it to 0.263. When you do homework, it will tell you the number of decimal places you've got to run stuff to. What we need next is the standard deviation. The more decimal places you have, the better things will be. So that's what we have. 4 decimal places, all 3 decimal places. Good so far? Okay. Ideally, what should I get for the average difference? The word being ideally. What do I want this number to be? Aunties? 0. Is it going to be possible? No. So I am getting a difference of 0.263, but just because I have the difference doesn't mean it's a significant difference. Did you have a question?
Yeah, so like for the data on the side there, we rounded to 2 decimal places, but then, when we know whether to round it, like which number?
The problem will tell you, my rule of thumb is the more decimal places you have, the better. When it comes to statistics such as mean, standard deviation, 2 to 3 decimal places. But when it comes to probability, I always say 4 or more. Always. So, any questions so far? Is it going to be significantly different? No, it's not going to. We'll see what. So, almost there. If that has the notation S of M, S of M stands for standard error. Of average difference. Let's see if you paid attention last time. What is the difference between standard deviation and standard error? So, very good. Now,
The root of n,
the root of n, and where does it go?
it's divided by.
Root of n. Very good. So, I'm not judging. S over square root of n. So 0.5975. What we have is it. What is n? N is the number of participants or sample size. Square root of 8. 2 decimal. Let's do 3 decimal places. What do we get? Point 3. Two, 1, 1, okay. 0.211. Good. Okay, so we have the standard error for the average difference. We have the average difference from the sample. In our steps for hypothesis testing, the next step would be to find the test statistic. Yes? Yes.
I'm a little bit confused on like units, if we're gonna be like required for units, or like if you would just put like degrees Fahrenheit there for the 0.211.
That is a great question. Do you follow it? So the average difference will have the same unit as temperature, degrees Fahrenheit. Same for standard deviation, same unit. Standard error will also have the same unit. But the test statistic will not have a unit. Okay, so I'll put a note here. The test statistic is unitless, that's why we call it a t-score, z-score, etc. The sample average difference minus the value mu that you claim divided by the standard error. That is a formula, you don't have to memorize it, put it in your cheat sheet. So m minus mu divided by standard error. So I know what m is, 0.263. What is the value that I claim? Well, no difference, or there is a difference. In this case, 0. It is in the claim itself, divided by 0.211. You can round to 2 decimal places. Tell me what you get. One point two. After rounding. 1.25. What we have is a t-score. It is unitless. So t-score simply means we use a t-distribution. Good. So here we are going to use t-distribution with degrees of freedom n minus 1. N is 8, 8 minus 1, I've got 6. Do we know what step 4 is? You can look in the notes. Go ahead. Sue.
Test statistic or test score using the same.
Okay, compute test statistic, test score. I guess I combined 3 with 4 and simplify towards.
Compare the test statistics to critical values.
Okay, we'll just change so that we are consistent. So here we are going to come up with a cutoff. So we have the data, we computed test statistic. We're going to come up with a cutoff. Cutoff is going to tell us whether to reject the null or not reject the null. What function in the calculator should we use to find cutoff? Hint. Look at the letter I'm using for the test statistic. Very good. Inverse T. We went over inverse T. So Mantis 8.05 earlier. Since it is a two-tailed test, what is the area of that shaded region under the curve? From way backward, value. Half of alpha, so 0.05 divided by 2. Once you give me the critical value, we'll know the answer. From last time or the time before. Second, Mars. Option number 4 is inverse T. It doesn't matter whether you put the area below on the left tail or the right tail. You can just switch the sign at the end to get the appropriate critical value. I'm simply going to go for the area that I shaded under the curve, the left hand side, 0.025 followed by 7, which is simply degrees of freedom, enter, negative 2.3646, I'll call it negative 2.365. If that is the critical value on the left hand side, what is the value on the right hand side? Positive, that easy. While we are here, let's go ahead and compute the probability for the p-value. So option number 6, it says T, C, D, F. So do not put the critical value in there, which is why I'm doing it side by side. You've got to put in the absolute value of the test statistic. So our test statistic is positive to begin with, 1.25. Yes,
Sorry, I was looking down for a second. How did you get to the TCDF?
press second bars and option number 6, I believe. Is it? 1.25, comma, second, comma, so blue button followed by, comma, 99. So E99 stands for infinity, and the last value would be 7, the degrees of freedom. So TCDF, first argument in this case would be the absolute value of the test statistic, E99, degrees of freedom, enter, I get 0.1257. That is a probability. Write that down. Good. So this number that I got using inverse D, negative 2.365. Yes. If this is negative, that is positive. So the data is giving us 1.25, correct? So 1.25 is over there. Did the test statistic fall in the rejection region? Yes or no? No. first observation that we make. Test statistic doesn't fall in the rejection region. Number two, p-value. I'll write the syntax here so that you know. How to calculate. I'm going to multiply it by 2 because this is a two-tailed test. So 2 times TCD, we put in the absolute value in the calculator, 1.25, E99, 7. And that number ended up being 1257. So whatever the calculator gave you, you are multiplying it by 2. We've come to 2 steps, very last step. Test statistic does not fall in the rejection region. So should you reject it? No. No. So do not reject, no. P-value is 0.2514. The easiest explanation that I have for p-value is the probability of type 1 error, mistaken rejecting the null based on the evidence, is in this case 0.2514. So I already know not to reject, but can you come to the same conclusion with the p-value? It is the probability that you make a mistake, specifically type 1 error, based on the data. So pay close attention. If I rejected the null based on everything that I've observed and done, the chances that I would be wrong is 25%. Good? So should I reject the null? If I knew that the chances that I would be wrong is 25%, should I reject the null? Well, no, I wouldn't reject the null if this is telling me that the chances that I will be making an incorrect decision is 25%. That doesn't make you smart, does it? If someone tells you there's a 25% chance that your marriage is not going to work, and then you go ahead and get married. Does that make sense? So, p-value is also giving you the same conclusion, but the easier way to check p-value it is not less than 0.05, which is simply the value of alpha. Good. So 25%, 5%. Both end up telling you that you should not reject the null. If I should not reject the null, do I find evidence to support the alternative? Yes or no? No. Can I say that there is a significant difference statistically? No, because I cannot reject the norm. So whatever difference that I saw here is not significant. Yes? Part two. If statistically there is no difference between the first child and the second child, can I say that the thermometer is reliable? That is, it is consistent? Agreed. So the answer is yes, it is reliable.